Good evening, everyone. Thank you so much for joining us tonight. My name is Kate Bruns, and on behalf of Harvard Bookstore, the Harvard Division of Science, and the Cabot Science Library, I am very pleased to welcome you to our program tonight with Adam Becker discussing his new book, What is Real? The Unfinished Quest for the Meaning of Quantum Physics. In just a moment, I'll turn you over to Melissa Franklin of the Harvard Physics Department, who will introduce the program this evening. But first, I'd like to take a quick moment to tell you about the Cabot Science Book Talks, a new collaboration between the Harvard Division of Science, the Cabot Science Library, and Harvard Bookstore. The series features talks throughout the academic year by the authors of recently published books on a variety of science-related topics. And we will soon announce our talks coming up after the holidays, so stay tuned. To learn more about the Cabot Science Book Talks and to learn about Harvard Bookstore's many other upcoming events, you can visit us online at harvard.com and you can sign up for our email newsletter. Tonight's talk will be followed by some time for your questions, after which we'll have a book signing and refreshments in the Cabot Science Library just outside this room and across the Science Center entryway. We also will have copies of What is Real for sale in the library as well. And as always, you have our thanks for buying books from Harvard Bookstore. Your purchases support this author series, and they really do ensure the future of a local independent bookstore, so thank you. And finally, just a quick reminder to silence your cell phones before the talk begins this evening. So now I will turn things over to Professor Melissa Franklin.
So hi, thank you for coming on a snowy, not quite snowy night. It's very nice to see everyone. How many people here are not paid by Harvard? Yes, thank you so much. Thank you so much for coming. When we talked about this book series, we thought of who we could bring here, and we went through all the books that were about to come out, but then some people in my department kept saying, well, what about this guy, Adam Becker? His book had already come out, but everybody decided that he was way too interesting to wait for his next book. So I'm really excited. Adam started at Cornell and did his PhD in cosmology at University of Michigan. And then he thought, I think I'll write a book. And so he's now a science journalist and author and speaker. And he's really interesting. And he's going to talk about some part of quantum mechanics and the way people think about it. And I just wanted to tell you ahead of time that I think I was one of the bad people. So when you're trying to think of the bad people when he's talking, you can think of me. What's going to happen is Adam's going to give his talk, and then he's going to be in conversation with Jacob Berendes, who's a physicist in the physics department, who is also very interested in this topic and teaches this incredible summer course to high school students, in case you have any children who want to go. It includes an introduction to theoretical physics that includes quantum mechanics, and it's very, very exciting. And he also has many, many other hats. He's the director of graduate studies for science at Harvard. So they're going to talk a little bit and then open for questions for anybody here. So here we go. Adam Becker. Let's go.
There we go. Hi. I'm going to start by turning on the microphone. Seems like a good first move. Hi, can everybody hear me okay? Yeah, great. Okay. Thank you, Professor Franklin, and thank you to the Harvard Bookstore as well for helping to sponsor this event. I'm really excited to be here tonight, and I am amazed and somewhat intimidated by the number of people in this lecture hall. When I first saw this hall earlier today, I thought, okay, well, this won't be full. And it's not, but it's closer to full than I expected. Significantly closer. So now that the pressure is on, let's talk about quantum physics. But thank you to all of you for being here tonight and choosing to spend your spare time talking about quantum physics. As Professor Franklin said, I'm Adam Becker. I am a science journalist and astrophysicist. And yeah, let's talk about the trouble with quantum physics and why it matters. So first, the slide that I just turned away from. Quantum physics works. And I really, really hope I don't have to convince anyone in this room of this fact. Quantum physics works phenomenally well. By almost any measure, it is the most successful scientific theory of all time. Quantum physics explains the world of the ultra tiny, the very, very small, but its impact goes far beyond the world of the very small, and it explains a great deal of the phenomena in our everyday lives and its impact on the technology of the last 90 years since it was first developed is so huge it's difficult to quantify. Quantum physics explains why the sun shines. It explains why we can see that the sun shines. It explains why you're not passing through your seats right now, why your bones and skin remain solid. It explains the nuclear hearts of the most distant space probes and the lasers at the supermarket checkout scanner. Quantum physics powers, I think, every single component of the AV system that we're using in this auditorium right now, and probably the lights as well. So quantum physics definitely works to a phenomenally high degree of precision. But there is a problem. If there were not a problem, I would probably not be here right now. So what's the problem? Well, the problem is that quantum physics, to a first approximation, the problem is that quantum physics is a bit odd. And what do I mean by that? Well, quantum physics is the physics of ultra-tiny objects. It explains how they behave, where they're going to be, what they're going to do. And the physics that we have for the world around us, for medium-sized dry goods, right? That's Newton's physics mostly. And Newton's physics says that if I want to describe where this clicker is, then I just need 3 numbers, right? I need 1 number for how far off the ground it is, 1 number for how far in front of me it is, and 1 number saying how far off, the center line that the origin that I define it is. But in quantum physics, if I want to say where an electron is, I can't do it with 3 numbers. I need more. In fact, I need an infinity of numbers scattered across all of space to describe the position of that electron. And that infinity of numbers is known as a wave function. And wave functions, like the name describes, they wave, they undulate smoothly. They don't change suddenly from one moment to another. They obey a very nice equation called the Schrödinger equation, which sort of looks and smells like a law of nature. And that's what they do. They behave kind of like waves. But that's already a little bit odd, right? Because an electron is one thing. Why do I need an infinity of numbers scattered across all of space to describe where it is? But it gets worse, actually. So I said that wave functions obey the Schrödinger equation. That's not quite true, or at least it's not true all of the time, or it doesn't appear to be true all of the time. Schrödinger equation says that wave functions wave and undulate smoothly, except sometimes when we look at something, when we measure something, the Schrödinger equation appears to be temporarily suspended. And the wave function of an object goes to 0 discontinuously, suddenly, everywhere, except for the spot where you found the object. And then the Schrödinger equation resumes. And this is very strange, especially if we think of the Schrödinger equation as a law of nature. Why should a law of nature depend on whether or not we're looking? And what do we mean by looking? What constitutes a measurement anyway? Does it only work when I do it? If so, why am I talking about quantum physics with a bunch of people to whom it doesn't apply? Do you have to have a PhD? I don't think so. Do you have to be alive? I don't think that matters either. I think that there were wave functions way back 13.8 billion years ago in the early days of the universe, and I don't think anything was alive then. But what do we mean by measurement, and why does it matter? So this gets a special name. It's called the measurement problem. So it's tempting in light of the measurement problem to say that wave functions are probabilities. That the wave function says, well, this is the probability that you're going to find the object you're looking for in a particular spot. But it can't quite be that simple, right? Because part of the problem is, what do we mean by find? What do we mean by measure? It's odd to have a word as poorly defined as measurement show up in what appears to be fundamental laws of physics applying to fundamental particles. But there's more to it than that. There's another problem with just saying it's a probability, which is that wave functions appear to perform tricks that simple probabilities don't have the ability to perform. So, for example, wave functions can interfere. They can do things that physical waves appear to do. They can diffract. And that's a bit odd for a probability to be able to display those sorts of physical phenomena. It means that if we can find a way of saying that a wave function is just a probability, then we need to do a little more work than just saying, oh, it's a probability. We have to think a little bit harder about what that means. And there's also another problem, which is, what the heck is going on before we look? Even if we find a way of defining what it means to look at a particle, what's going on before we look at it? Surely its existence doesn't depend on whether or not we're looking at it. And this brings us to the most famous form of the measurement problem. Schrodinger's cat, right? It's a talk on quantum physics for a wide audience. I have to talk about Schrodinger's cat. There's actually a law, I think at least in California, I don't know about Massachusetts. So how does this work? You seal in a box a cat, which is already an impressive feat. But you also throw in a lump of very slightly radioactive metal, something that's only going to emit some sort of radiation, maybe on average about once every half hour. And you throw in as well a Geiger counter to detect radiation. And that Geiger counter is sort of rigged up to a kind of Rube Goldberg contraption. There's a hammer that's going to fall if the Geiger counter gets tripped, if it detects radiation. And then that hammer will smash a vial of cyanide. And cats don't respond well to cyanide. So if the radioactive metal emits radiation, then the cat will die. So this is Schrodinger's cat. This is what you seal in that box, and you leave it in there for, say, 15 minutes, long enough that there's about a 50-50 shot, according to quantum physics, that a chunk of radiation will go flying off the radioactive metal, and so there's a 50-50 shot that when you open the box, the cat will be dead or the cat will be alive. Now, small objects, they can behave maybe in different ways than big objects. You know, the fundamental problem with quantum physics is not just that it's strange, but that it's strange in this problematic way that leads to the measurement problem. Strange behavior in and of itself is not a problem for physics. There's all kinds of strange behavior. The world is a wild and woolly place. Maybe fundamental particles can be in some sort of indeterminate state where they're both emitted and not emitted before you look. But cats are either dead or alive. Cats are not somehow both dead and alive. And this is what Schrodinger himself was driving at when he put together this thought experiment. He wasn't trying to illustrate a cool feature of quantum mechanics. It wasn't a feature, it was a bug. He was saying, this is a wonderful theory that works incredibly well, that describes so many things so phenomenally accurately, but we're not done yet. There's a problem, and we need to address that problem. And he put together this thought experiment to try to get at what that problem was. He said, it is ridiculous to think, this is not a direct quote, but he said something along the lines of, it's ridiculous to think that the cat is neither dead nor alive until we open that box and take a look at it. Even though that is the traditional answer to the question of what's going on with a small particle described by a wave function before we measure it. So he said, you can't deny this. And yet, of course, this is exactly what some of his contemporaries denied. That's Niels Bohr there on, I guess that's the right as you look at the screen, and Werner Heisenberg on the side of him there on the left. two of his contemporaries who said, no, this is not a problem for quantum physics. They denied that you need to have an account of what's going on with the cat before you open the box. Now, there were various responses to Schrodinger's concerns. Some people said, oh, what's going on in the box before we open it, that is, in principle, not something that we can know anything about, because you're asking what's happening before you look. And something that we, in principle, can't know anything about, that's not in the domain of physics. That's not our job. We don't need to worry about that. Other people said, oh, well, you're taking quantum physics too seriously. Quantum physics isn't a theory of how the world actually works. It's just a theory that tells us what the outcomes of measurements are going to be. And in this case, it tells you that there's a 50-50 shot that the cat will be alive. And that's exactly what we see. If you were some kind of monster and you did this experiment over and over again, you'd get 50% of the cats alive and 50% dead, and also hopefully arrested. So that's what some other people said. And other people said, oh, well, but quantum physics, that's just for small stuff. We don't need to worry about the effect that quantum physics is going to have on cats. Quantum physics is something that only applies to the world of the very small. This is not a position that I think is terribly popular among physicists today, but this was 1935. Quantum physics was only just about a decade old. And there were definitely some people who responded in this way, saying, somewhere between the atom and the cat, quantum physics is going to have to break down in some way or become an approximation. And this is not an unreasonable position on the face of it, because remember, cats are made of a phenomenal number of atoms, about, something like 100 trillion atoms in the average house cat. So that's a lot. And this collection of sort of assorted, vaguely related claims came to be known over time as the Copenhagen Interpretation of quantum mechanics, named after the home of Niels Bohr's famous institute in Denmark. And the Copenhagen Interpretation says, we don't need to think about what's going on in the box before we open it. We don't need to worry about things like the measurement problem, because we don't need to regard these things that the theory describes as real. What is real? That's not a question for physics. We don't need to worry about that. What matters is that the theory works incredibly well. Or some people said, yeah, questions about what is real, those do matter, but they're not the job of physics. Other people said, oh, no, those questions are actually meaningless. You can't define what's going on there. You're asking nonsensical questions. It's like asking about the marital status of the color blue. It's just a nonsensical question. These sorts of positions came to be known as the Copenhagen Interpretation. And the slogan that was developed many decades later for the Copenhagen Interpretation, but I think accurately describes the attitude taken by a lot of people who adopted the Copenhagen Interpretation, was the quote from the physicist David Mermin, "Shut up and calculate." And despite the fact that this may sound somewhat silly, there's a great deal of virtue in shutting up and calculating. Shutting up and calculating is a wonderful thing to do when you have a phenomenally useful and accurate theory that appears to have some sort of conceptual problem at its foundation. You can, bash your head against that conceptual problem, or you can, get on with solving problems that seem more interesting or amenable to you. And you can make a lot of progress this way. So there's not a real problem with shutting up and calculating per se. The problem is when you promote it to the official thing that everyone must do. When you say, no, it's wrong or useless or a waste of time to try to do anything other than shut up and calculate. That's when there's a problem. Because if you say that quantum physics is just, some sort of instrument for describing outcomes and experiments and observations in the world around us that has nothing to do with the world, then you have a variety of problems. The first problem that you have is you've robbed the theory of all of the wonderful explanatory power that we talked about before. We said it explains why the sun shines, right? I said it explains why our eyes can see, why we're not passing through the floor. Well, if it's just an instrument for predicting outcomes, it doesn't tell us why anything happens. It just says you're not going to pass through the floor. Don't ask why. Shut up and calculate. Shut up and don't pass through the floor. Also, if it's just an instrument for producing predictions about the world, it's a phenomenal miracle that the theory works at all. If the mathematical quantities and entities in the theory have nothing to do with the stuff in the world around us, then what are the odds that this complex assemblage of mathematical objects would actually correctly predict anything, much less be, the most phenomenally accurate theory of all time? So that's another problem. Another problem is this just isn't how we talk about any of the other theories that we have in physics. With very few exceptions, I think most physicists believe that electromagnetic fields are a thing in the world. We believe that there's a thing called general relativity, which that space-time warps, and this ensures that balls will roll down inclined planes at the correct speed. We don't talk about statistical mechanics as a theory that just issues correct predictions of the world. We think that there is, in fact, 10 to the 23 atoms in this USB dongle, and that by knowing that there are so many atoms in that USB dongle, we can correctly predict how it will respond when we slightly increase its temperature in one spot. We think that that's why things like the diffusion equation work. We don't talk about these things the way that we talk about quantum mechanics. So that's a little bit weird. And speaking of other branches of physics, good luck doing cosmology if there's a fundamental line between the quantum world and everything else, because cosmology is supposed to be the study of everything on big enough scales that we don't have to worry about the small things. Right? And small things here being anything smaller than a galaxy cluster. But quite seriously, that's what cosmology is supposed to do, but we want to be able to do quantum cosmology, right? And there are plenty of people who do it quite successfully. So we don't want a dividing line like that. And of course, there's no experimental evidence for any sort of dividing line like that. So these are the problems. Now comes the part of the talk where I need to give you a warning. Actually, two warnings. The first warning, raise your hand if you don't have a degree of some sort in physics or astronomy. Excellent. Oh, this is fantastic. Wonderful. Okay, so then these warnings are very necessary. The first warning is, this is not the standard line on quantum physics that you will get from most physicists. Okay, I am giving you a bit of an alternative, maybe a subversive view, right? And I think it would be remiss of me not to say that in a public talk like this, especially where so many people do not have training in physics. So this is not the standard line. So why do I sound so confident about it? Why am I standing up here grinning, right? Well, I will say that the standard line on quantum physics, which is sort of more in line with this Copenhagen interpretation that I've been talking about, one of the reasons that you shouldn't believe it, aside from all the stuff that I said, is that the usual way it is presented to students of physics comes along with a historical narrative about where quantum mechanics came from and where the Copenhagen interpretation came from. And that historical narrative is, I'm going to say, not completely correct. I'll go into a little bit more detail, but it's mostly bullshit. So, which brings me to the second warning. The best psych research out there, my understanding of it, I'm not a psychologist, says that if you want to debunk something, you shouldn't present the myth and then the reality, because presenting the myth actually reinforces it in people's minds. I'm going to ignore that advice. I'm going to present to you this historical myth, and then I'm going to explain why it's wrong. And so I'm going to give it to you in a kind of cartoonish way. If you want to accuse me of constructing a straw man just so I can kick it down, feel free. But I do think that those of you in the audience who are physicists will recognize something in this myth that I'm about to put up there. It should sound pretty familiar. So this is the myth. This is what didn't happen. Once upon a time, a collection of brilliant physicists in the first quarter of the 20th century put together a theory called quantum physics. And these physicists included people like Niels Bohr, Werner Heisenberg, Wolfgang Pauli, whose back is to the camera, but this is pretty much the only picture I could find of the three of them together. And also, other people such as Max Born and Louis de Broglie and many other names that are familiar to basically every physicist alive. One of the other people who constructed this theory was Albert Einstein. He played a role in the early development of the theory. And the theory said that the world was fundamentally random, that there was no way to deterministically predict the outcomes of experiments. You could just predict probabilities. You couldn't do better than that. And that was a fundamental feature of nature, as was the fact that when you're not looking at things in the quantum world, they're not real, and somehow our observations bring about the existence of these objects. And Einstein, he had been a bomb-throwing revolutionary in his youth, but now in the development of quantum physics, once it came to fruition, he was older. He was not at the full height of his powers. He was starting to go a little bit mentally, and so he was not able to accept these revolutionary new ideas that were just as revolutionary as the ideas that he had introduced in his youth with relativity. And in particular, Einstein could not accept that nature could be random. It had to be deterministic. It had to be like clockwork for him to accept it. And he said, God does not play dice. And so he came up with a set of thought experiments that he presented to Niels Bohr, the informal godfather of this collection of brilliant physicists. And he presented these thought experiments to Niels Bohr to try to get around one of the fundamental tenets of quantum physics, the uncertainty principle, which says that you can't know a quantum object's position and momentum to arbitrary certainty. So Einstein came up with a variety of these thought experiments meant to get around that uncertainty principle and a couple of others, and this culminated in a particularly embarrassing episode in 1930 where Einstein came up with a thought experiment to get around what's called the energy-time uncertainty relationship, involving a strange contraption with a clock in a box full of light hanging from a spring, and he gave it to Niels Bohr, and he said, this contraption that I've sketched on this piece of paper, it shows that it can't work, and Bohr was tearing his hair out, but then the next morning saw Bohr's triumph, and he showed that Einstein was wrong because he'd forgotten his own theory of general relativity. And so Einstein went home in deepest humiliation, and a few years later, finally came back with a different thought experiment. He said, this thought experiment, which he came up with two colleagues named Podolsky and Rosen, called the EPR thought experiment after their initials. This thought experiment shows that if the way you think about the world is right, then there must be spooky action at a distance, instantaneous connections between far distant objects, and that just can't be how the world works. There's no way that you can be right, Niels Bohr and everybody else in physics. But Niels Bohr responded and said, no, everything is fine. There doesn't have to be something like spooky action at a distance. And this was left as a philosophical puzzle for 30 years, until after both Bohr and Einstein were dead, a heroic physicist named John Bell came along, and he proved that the difference between Einstein's position and Bohr's position was a matter of experiment. You could prove in the laboratory which one of them was right. And so the experiment was done, and Niels Bohr was shown to be right, and Albert Einstein was shown to be wrong, and the world was safe for quantum mechanics, and everybody lived happily ever after. The end. So, how much of that is true? Well, not a whole lot. It is certainly true that a brilliant collection of physicists in the early 20th century came together and constructed quantum physics. It is certainly true that Niels Bohr, Werner Heisenberg, Wolfgang Pauli, and all the other people I mentioned were part of that team. It is also true that Albert Einstein was one of those people as well. It is also true that in 1926, when the first full theories of quantum mechanics were put together, Einstein looked a little more like this. He was in his 40s. He was fine. And his real problem was not that quantum mechanics was random. He didn't like that. But His real issue was twofold. He felt that quantum mechanics lacked a concept of reality independent of the observer. He did not think that the world doesn't exist unless people are looking at it. He compared this to the philosophy of George Berkeley. He said, to be is to be perceived. That's nonsense. And he also said from the beginning that quantum physics seems to involve strange long-distance connections. In fact, he said this as early as 1909, well before any full theory of quantum physics was developed. And he was really unhappy about both of these things. The concerns about the randomness in quantum physics were completely secondary to those primary two concerns, and his letters and writings make this explicitly clear. And there's consensus on this from historians of physics. So Einstein did indeed come up with a series of thought experiments, but most of them were meant to demonstrate these two problems, in particular the problem with long-distance connections. Einstein felt that physics had to be local. There couldn't be instantaneous connections. And so these experiments were about his concerns about locality in quantum physics. And indeed, that's what this thought experiment was about. It wasn't about getting around the energy-time uncertainty relationship. Niels Bohr completely misunderstood what Einstein was getting at, and this is shown by letters between Einstein and Ehrenfest and Bohr at the time in 1930. Einstein was not concerned about the energy-time uncertainty relationship, and Bohr just sort of completely missed the point. Not only that, but even if Einstein had been concerned about the energy-time uncertainty relationship, Bohr responded to the thought experiment that he thought Einstein was giving him by invoking general relativity, which is a theory that we still don't know how to make work with quantum physics. So that's not an acceptable response if what you want to do is defend the internal consistency of quantum physics. There's a different response you can give to the argument that Bohr erroneously thought Einstein was giving him, but that was not the response that Bohr gave. So this should have been a massive humiliation for Niels Bohr. It didn't quite go down that way. Einstein did put together a thought experiment called the EPR thought experiment. He did say this shows that there's some sort of spooky action at a distance. I think the next slide is Einstein. Let's find out. Oh yeah, this is Einstein and Bohr debating. And actually that picture was taken by Paul Ehrenfest somewhere around 1930s. So he did in fact come up with this EPR thought experiment. He did say it was about spooky action at a distance. Specifically, he said this thought experiment shows that in quantum physics there is a forced choice. You can either say that quantum physics is a complete description of everything that's going on, meaning that you can't talk about what's happening in the box before you open it, or you can say that it's local. Those are your choices. So you can get rid of spooky action at a distance, but only at the price of saying that there's something missing from the theory. It works incredibly well, and everyone, including Einstein, agreed on that. But you have a choice, and you need to pick one or the other. Bohr's response to EPR, which that part of the story is true, he did respond. I'm going to say that that response is a bit unclear, which is an understatement. When I first read it back in college, I went to the professor I was talking with about all this stuff at the time, and I said, do you know a better translation of this? And he sort of chuckled to himself, and he said, no, Adam, this was written in English. And Bohr's English was pretty good. That's just how it is. In fact, Bohr himself apologized later in life for, I think he said, the infelicity of expression in his response to the EPR paper, but he didn't then go on to clarify what he meant. He just kind of kept going. Bohr is difficult to read, and I recommend going out and trying it yourself to confirm that. There is almost no consensus among scholars of Bohr about what he meant. Which is not to say he didn't have a coherent position, it's just to say we don't know what it is. I don't pretend to know, at least. Maybe someone knows. So, then what happened? Well, physics just kind of moved on. despite the fact that Einstein had shown this problem and that Schrödinger had actually chimed in with his problem of the cat, which actually appeared in his enthusiastic response to the EPR paper saying, yes, this is a problem, and also so is this cat. Despite this, most physicists just kind of moved on, and there was a variety of reasons for this. I could be cute and say I could write a book about it, but one of the reasons was, there was a lot of great work to be done with the theory, even though we didn't fully understand the problems at the heart of it. But another reason was a proof from John von Neumann, possibly the greatest mathematical mind alive at that point in the 1930s. He had put together a proof in his famous quantum mechanics textbook that, in fact, you could not find a way around this randomness in quantum physics. You could not add something to the theory to complete it in the way that Einstein had in mind. And this proof from this great mathematical mind was taken very seriously by a lot of people. Unfortunately, the proof was wrong. There was actually just a mistake in the proof. It's not that the proof was logically incorrect, it just didn't show what von Neumann thought it did. And the first person to point this out was actually the mathematician and philosopher Grete Hermann, who just within a few years of the publication of von Neumann's proof in 1932, she said, well, look, there's a problem here. This proof doesn't work the way that von Neumann thinks it does. It doesn't show what he says it shows. But she was, by and large, not really listened to. Part of the problem was that she didn't actually disagree with von Neumann's conclusion. She just disagreed with how he got there. She said, oh, yeah, he's right. You just can't prove it mathematically. And another part of the problem almost certainly was that she was a woman, and that she was working in mathematics in the 1930s when women, by and large, were not even allowed to work in universities lecturing mathematics. So her work was mostly forgotten. A few people knew about it, but didn't seem to really care. There were stories that Einstein was aware either of Hermann's work or at least of von Neumann's proof and the problem with it. I'm not so sure that those stories are to be trusted. But anyway, so things just sort of went along, and there was a world war in which quantum physics played a pivotal role. And people kind of forgot about this for a while. And then in the 1950s, very early 1950s, a young physicist named David Bohm, who's working at Princeton, came up with an entirely different way of thinking about quantum physics. He said, oh, we don't have to say we can't talk about what's going on before we look. He said, we can absolutely talk about what's going on before we look. There are particles and there are waves. And the waves guide the motion of the particles. And when you look, you disturb the waves, and that changes the way the particles behave. But they're certainly there whether or not you're looking. And this seems completely reasonable, but there were a few problems. The first problem was that he could only make this work for part of quantum physics. He couldn't find a way to make it work for the relativistic extension of the theory, relativistic quantum field theory. And that was a big problem, but he was working alone, and that's a big job. So maybe cut him some slack on that one. You should also cut him some slack because at the same time he was doing this, he was going through a sort of personal legal hell. He had been a member of the Communist Party very briefly in the early 1940s when he was a graduate student at Berkeley. He went to a couple of meetings and then he left because he said the meetings were boring, which I find surprisingly easy to believe. But nonetheless, the Army and the FBI and the US Congress did not look too kindly on a physicist who had gotten his PhD with Robert Oppenheimer having ever been a communist. And so he was called up in front of the House Un-American Activities Committee in 1949, which at the time was chaired by this ridiculous asshole who you may have heard of named Richard Nixon. And he was asked a bunch of questions and asked to name names. He did not name names because David Bohm had, integrity. Instead, he pleaded the First and Fifth Amendments, right to free assembly, right to not incriminate himself. And then he went home and thought that it was all over. But a year and a half later, he was arrested on contempt of Congress and then blacklisted and fired, well, not fired from his job at Princeton, but it was not renewed, even though by that point he had been found not guilty in a court of law, because as it turns out, there is a First and a Fifth Amendment to the United States Constitution. So Bohm, while he was going through all of this, like between his arrest and his day in court, he came up with this interpretation, this new way of thinking about quantum physics with particles surfing on waves. And then he was blacklisted, and he couldn't find work anywhere except for Brazil, even though he had recommendation letters from Albert Einstein and Robert Oppenheimer. So if you're having trouble finding work, feel a little better about it. You're not the only one who's ever had that problem. So he came up with this thing, and this flew in the face, quite obviously, of von Neumann's famous proof, but it wasn't entirely clear where von Neumann's proof had gone wrong, except to Greta Hermann, and no one was listening to her yet either. And so it took another person to actually figure out why von Neumann's proof was wrong and explain it to everyone. He was convinced that it had to be wrong the minute he saw Bohm's papers. He knew that they were fine, even though people were still dismissing Bohm's ideas by citing von Neumann's proof. And this person who rediscovered the problem with von Neumann's proof and made the rest of the world aware of it was one John Bell. John Bell, who hated the Copenhagen Interpretation, he said it was rotten. I think an intentional reference to Hamlet. So John Bell found the flawed premise in von Neumann's proof, showed that it in fact was a proof of something entirely different, known as quantum contextuality, and then he stared at Bohm's interpretation of quantum physics for a long time and thought about the EPR problem for a long time, and eventually he found a truly profound result known as Bell's theorem, which does not show that Einstein was wrong and Bohr was right. It showed that Einstein was completely right to be worried about long-distance instantaneous connections, because Bell's theorem basically shows that either there are long-distance instantaneous connections in nature, or quantum physics is wrong in some laboratory situations. Now, explaining how he showed that would take another entire lecture and probably longer than 45 minutes. I do have an explanation of it on my website that involves, this animated GIF is not loading very well. It involves roulette wheels. If you're curious about how Bell showed that, there's a sort of interactive explanation of it over there. The other thing that happened after all this is that there were more interpretations found. For example, Hugh Everett. Let's see yes, there we go, Hugh Everett. Hugh Everett, a graduate student in physics at Princeton University in the mid-1950s after Bohm had been exiled to Brazil. And I forgot to mention, Bohm was also trapped in Brazil. The US consulate in Brazil confiscated his passport, so he couldn't leave for 4 years. He eventually got out, but that's a different story. So while Bohm was trapped in Brazil, Hugh Everett showed up at Princeton and came up with an entirely different way of thinking about quantum mechanics. He proposed that, in fact, the wave function is everything, and that it never collapses, and that the cat is both dead and alive before and after you open the box, and when you open the box, you split into both a copy of you that sees a dead cat and a copy of you that sees a living cat. And this sounds completely wild, but actually has a fair amount of support in the mathematics of quantum physics, and again, explaining that would be an entire other lecture. His work was completely forgotten for over a decade. The depths of deepest obscurity in academic history, one person said. He was probably exaggerating about that, but in any event, people just continued to not think about these things for a long time, and it was not until the second generation of experimental tests of Bell's theorem in the 1980s that people started to pay more attention to these foundational questions. And it is still the case that there are rampant misunderstandings of the measurement problem and of all of the many interpretations of quantum physics, and now there are many of them, and just naming them would probably take me 45 minutes. Rampant misunderstandings of Bell's theorem and all of this. This is a subject that is difficult to get one's head around, and the history in particular is often misrepresented, and this is my attempt to get the record straight. But there is another sort of harder question here, which is, who cares? Why does any of this matter? After all, quantum physics works, right? We all agree. Raise your hand if you don't think quantum physics works. Good. Yeah, quantum physics works. That's not really up for debate. So given that it works, why does any of this matter? Why does it matter, what the theory says about the world around us? Why should we care as, people in the world who are not physicists? For that matter, why should physicists care? If the theory works, doesn't that mean we can just sort of get on with our lives? Well, that's a really, really good question, and I'm going to need to appeal to a higher authority in order to answer it. So I give you Richard Feynman.
Now, another thing that people often say is that for guessing two identical theories, suppose you have two theories, A and B, which look completely different psychologically, have different ideas in them and so on, but that all the consequences that are computed, are exactly the same. Maybe say they even agree with experiments. The point is, though, that the two theories, although they sound different at the beginning, have all consequences the same. It's easy usually to prove that mathematically by doing a little mathematics ahead of time to show that the logic from this one and this one will always give corresponding consequences. Suppose we have two such theories, how are we going to decide which one is right? No way, not by science, because they both agree with experiment to the same extent. There's no way to distinguish one from the other. So the two theories, although they may have deeply different ideas behind them, may be mathematically identical, and usually people say then in science one doesn't know how to distinguish them, and that's right. However, for psychological reasons, in order to guess new theories, these two things are very far from equivalent, because one gives a man different ideas than the other. By putting the theory in a certain kind of framework, you get an idea what to change, which would be something, for instance, in theory A that talks about something that you say, I'll change that idea in here. But to find out what the corresponding thing is you're going to change in here may be very complicated. It may not be a simple idea. In other words, a simple change here makes maybe a very different theory than a simple change there. In other words, although they're identical before they're changed, there are certain ways of changing one which look natural, which don't look natural in the other. And therefore, psychologically, we must keep all the theories in our head. And every theoretical physicist that's any good knows 6 or 7 different theoretical representations for exactly the same physics, and knows that they're all equivalent, and that nobody is ever going to be able to decide which one is right at that level, but he keeps them in his head hoping that they'll give him different ideas for guessing. Incidentally, that reminds me of another thing, and that is that the philosophy or the ideas around the theory, a lot of ideas, you say, I believe there is a space-time or something like that in order to discuss your analysis, that these ideas change enormously when there are very tiny changes in the theory. In other words, for instance, Newton's ideas about space and time agreed with experiment very well. But in order to get the correct motion of the orbit of Mercury, which was a tiny, tiny difference, the difference in the character of the theory with which you started was enormous. Reason is, these are so simple and so perfect. They produce definite results. In order to get something to produce a little different result, it has to be completely different. You can't make imperfections on a perfect thing. You have to have another perfect thing. So the philosophical ideas between Newton's theory of gravitation and Einstein's theory of gravitation are enormous. The differences, rather, are enormous. What are these philosophies? These philosophies are really tricky ways to compute consequences quickly. A philosophy, which is sometimes called an understanding of the law, is simply a way that a person holds the laws in his mind so as to guess quickly at consequences. Some people have said, and it's true, for instance, in the case of Maxwell's equations and other equations, never mind the philosophy, never mind anything of this kind, just guess the equations. The problem is only to compute the answers so that they agree with experiment, and is not necessarily to have a philosophy or argue or words about the equation. That's true in a sense, yes and no. It's good in the sense you may be, if you only guess the equation, you're not prejudicing yourself and you'll guess better. On the other hand, maybe the philosophy helps you to guess. It's very hard to say. For those people who insist, however, that the only thing that's important is that the theory agrees with experiment, I would like to make an imaginary discussion between a Mayan astronomer and his student. The Mayans were able to calculate with great precision the predictions, for example, for eclipses and the position of the moon in the sky, the position of Venus, and so on. However, it was all done by arithmetic. You count a certain numbers, you subtract some numbers, and so on. There was no discussion of what the moon was. There wasn't even a discussion of the idea that it went around. There was only calculate the time when there would be an eclipse or the time when it would rise, the full moon, and when it would rise, half moon, and so on. Just calculating only. Suppose that a young man went to the astronomer and said, I have an idea. Maybe those things are going around, and there are balls of rocks out, like rocks out there. We could calculate how they move in a completely different way than just calculate what time they appear in the sky and so on. So, of course, the Mayan astronomer would say, yes, how accurate can you predict eclipses? He said, I haven't developed the thing very far. He says, but we can calculate eclipses more accurately than you can with your model, and so you must not pay any attention to this because the mathematical scheme is better. And there's a very strong tendency of people to say against some idea, if someone comes up with an idea and says, let's suppose the world is this way, and you say to him, well, what would you get for the answer for such and such a problem? And he says, I haven't developed it far enough. And you say, well, we have already developed it much further, and we can get the answers very accurately. So it is a problem as to whether or not to worry about philosophies behind ideas.
So, these things matter. They matter not just for doing physics, but for coming up with the next theory in physics. Because if we want to think about, what the next theory will be, how to go beyond our current theories, we need to have some idea of what our current theories are saying about the world. So it's helpful to us in that way. It makes a difference in that way. And it also makes a difference for the wider world. Remember, for the vast majority of human history, in many cultures, especially in Western cultures, this was the picture of the world that people had. The Earth was at the center, and everything revolved around us. And this certainly had a massive effect on the way that people thought about themselves and the world that they were in. And when we discovered that this was not true, this fundamentally changed a lot of things about the way that we related to the world. It was a massive revolution in our understanding of ourselves that went well beyond the world of astronomy and physics. If Copernicus hadn't uncentered the Earth from the universe, it seems doubtful that Darwin would have had the audacity to uncenter humans from biological creation. And if both Copernicus and Darwin had not done what they did, then Stanley Kubrick certainly wouldn't have been able to do what he did. So these things matter not just to physics, but to science and the rest of the culture of our world, a world whose every corner has been reshaped by science. These things matter. The pictures and stories that come with our best theories of the world matter. And understanding what is actually going on in the world is the project of science. So I've written a book about this. If you want to hear more about what I have to say about this and more about the stories about David Bohm and John Bell and Hugh Everett and the others, and there are many, many others and many strange, strange episodes, including Hugh Everett getting really, really drunk in the Princeton Common Room. If you want to hear these stories, I strongly suggest, humbly, that you check out my book. Thank you.
Incredibly great talk. Having us in conversation for 10 questions from the audience, and then buy books. Or if you want to leave now, you can buy books also. Or if you can buy books tomorrow. So, Jacob and...
Thank you.
Wonderful talk. Great.
Ran a little over.
Awesome. Great. So that was a wonderful talk.
Thank you.
My daughter overheard that lecture from Feynman some time ago, and she says, "Daddy, is that Bugs Bunny?"
Well, Wolfgang Pauli once said that Richard Feynman spoke like a gangster, which, yeah, kind of does sound like Edward G. Robinson a little, I guess.
Yeah. So I had a bunch of questions. I was going to take notes on a pad, but I don't have paper or pens anymore.
Oh, that's not good.
Yeah. So But I wanted to actually start with the epigraph of your book, and I read this book. It was wonderful. I cannot endorse it enough.
Thank you.
It's funny, as we were setting it up, people who heard about this talk were like, "Oh, you wrote that book? Oh, that's a wonderful book. I really enjoyed it." It was just one person after another, so I strongly recommend it. So you begin the book with an epigraph from Ursula K. Le Guin.
Yeah.
The soundest fact may fail or prevail in the style of its telling.
Yeah.
So I think given your talk and given sort of the book, this kind of makes sense, but maybe you want to elaborate a little bit on why you selected that quotation.
Well, part of it is just that I think Ursula K. Le Guin was one of the greatest writers in the English language ever. Yeah.
Good moment.
And I really wanted to find a way to put her in my book somehow. She's not particularly well known for her work on quantum physics. So, but yeah, I mean, that quote shows up, I think, on the very first page of The Left Hand of Darkness, or somewhere very close to the beginning. And that book, in some ways, sort of centers around what people will believe about the world around them and how that is shaped by the cultures that they live in and by their ideas about how the world must work. And I think that that's a lot of what's at stake in the history of quantum physics as well. I mean, there are these preconceived notions that people got from, different philosophies or different ways of thinking about the world that they brought to the table when they developed quantum physics, and these things sort of rang down the decades and influenced the way that we think about it now. Even though, at least to me, it seems relatively clear that there are unsolved problems at the heart of the theory, there are people who have spent their entire careers vigorously denying this, simply because, I think it's mostly a historical accident that the story about the world that went with quantum physics, or rather the lack of a story known as the Copenhagen Interpretation, happened to be the one that sort of won out in the political infighting that happened in the immediate aftermath of quantum physics being developed. And so, it was the style of telling people these unfortunate or uncomfortable things about quantum physics became basically what was at stake.
Yeah, so I think one thing that comes across especially in the book, so Niels Bohr, he comes across kind of like a villain in the book. I mean, he doesn't come across as someone with malice per se, although there are several characters in the book who do seem to...
You mean Nazis?
Yes. But even the context of just physics.
Oh well,
right?
Yes, yeah. You
Right.
mean Rosenfeld?
Right, Rosenfeld and other characters to a lesser extent. I mean, the way that for example Oppenheimer is depicted.
Well, he's more of a mixed bag, but no, I hear what you're saying. Yeah, I mean Bohr. I don't think Bohr was a villain. He certainly didn't seem to have any malice.
Right.
He was a brilliant physicist who made seminal contributions to this incredibly important theory, who also happened to be a very bad writer and public speaker, and had this philosophy of the world that he couldn't articulate clearly enough for people to be able to, independently reproduce it in a way that they would all agree with each other about what he was saying, and that ended up being very important.
Yeah, it's interesting. There's a comment you make in the book. You quote, I forget who it was, maybe it was Max Born, who said that it was impossible to describe Niels Bohr to someone who didn't know him. And it's just remarkable how and again, this is a testament to the quality, I think, of the book, but also to the incredibly interesting characters who led to this.
Oh, yeah.
They were an incredible assortment of idiosyncrasies, talents. Bohr was way at one end of being very unclear. Many of them were extremely clear writers, and so we have this incredible historical record. It's fascinating that he would have ended up in a position of such authority, given that he was sort of not always very clear in how he expressed himself.
Yeah, I mean, I think that happened for a variety of reasons, right? I mean, he was a brilliant physicist, and his insight into the structure of the atom with the Bohr model was unequivocally like this incredible breakthrough, and really helped lead the way to a full theory of the quantum world. he also apparently had this incredible personal charisma. I mean, I don't know that he's my favorite person in the book, but he might be the person in the book that, I would most want to meet that I didn't meet, right? Because it's so interesting to hear someone described as having this almost inhuman level of charisma. He also had a great deal of political power because he was this very prominent physicist in this small country that, ended up showering him with honors and money, and he was also a very collaborative person. He was apparently a very warm and kind individual who really liked to work with other people, and sort of built up a school around himself because he worked in this very social way. And I think that's like a really wonderful thing, and so that's sort of why I don't feel like Niels Bohr was a villain. I just think he was, deeply misunderstood and didn't do enough to clarify, and that ended up being really, really important. And I also think he was mistaken about some things.
It is fascinating because, there have been many great theories in the history of science.
Yeah.
I think it's remarkable, given the empirical success of quantum theory, that so many of the people who were instrumental in its early development came to have serious doubts about the foundations of the theory. And this isn't just Einstein, it's not just Schrodinger, but de Broglie.
Yep.
Even you look at people who, historically have been regarded as real stalwarts of quantum theory, like Dirac. But even Paul Dirac, who was mentioned a little bit in the story, Paul Dirac, for those of you who don't know, is one of the great titans of theoretical physics, on par with Einstein. During a span of years, starting in the mid-1920s and into the 30s, basically published like a paper working always alone, practically every year, introducing some staggering breakthrough in the theory. And he's often regarded as one of the people who defended the sort of very traditional, but when he gave a lecture later in his career talking about where he saw things, and his answer wasn't that we should ignore the problems of quantum theory.
Yeah.
His answer was that we should just wait until we replace it with a different theory.
Yeah, he definitely thought, okay, yeah, there are these unsolved problems at the heart of the theory, and we're not ready to address them. And that may well be true. It may be that we don't have the conceptual tools or experimental evidence we need to solve these problems, but they're there. Yeah.
So good. I mean, we're running a little past time.
Yeah,
We should
I
probably
ended up taking
take
more
questions
time
from
than I
people.
thought. Sorry about that.
Do we have a microphone going around? Yeah.
Yeah.
Thank you.
Yeah, you're standing up, so I have to go over there.
So I should ask first, how does quantum physics explain the existence of chi energy?
Of what?
Chi energy.
It doesn't.
But you said before that explains everything.
Yeah.
So there seems to be a flaw in your statements, but it's okay. Life is funny.
Great question.
Here's a question over here. So let's go back to Dirac.
Yeah.
Now, Dirac reconciled quantum mechanics with special relativity.
Yeah.
And
Can you speak into the microphone a little more?
He reconciled quantum mechanics with special relativity, and there's a Dirac equation, which took over from Schrodinger to some extent. And also he founded quantum field theory, which led to enormous problems mathematically, which Feynman did some work on.
Yep.
So the question is, how do you reconcile the entanglement, which is non-local,
Yeah.
with special relativity, which is local,
Yeah.
and Dirac's monumental contributions?
Sure. Yeah. I mean, this is a good question. The short answer is quantum field theory is a wonderful theory that is phenomenally successful, but it doesn't escape the measurement problem. You still end up having something analogous to a collapse of a wave function, and that's where this non-locality sort of shows up. So it doesn't evade the non-locality that shows up in Bell's theorem. And as for how to make that consistent with relativity, I mean, that's an open problem.
special relativity makes you pay a price for non-locality.
Yeah.
If you can communicate a signal, and I can define a signal, very concretely. A signal is the creation of a new correlation between systems. As I'm talking to you, as we're talking to you, and we're sharing information with you, your brains are, if we're doing a good job, becoming increasingly dependent or correlated with the states of our brains. The formation of those correlations is a signal. And in special relativity, when things can influence each other instantly at a distance, through some of this requires a little bit of technical discussion, it can happen that observers in different frames of motion can see the events happen in different chronological orderings. This becomes a problem if the interaction is a signal, because then you can create correlations, you can send information, according to some observers, backward in time. That's a problem. It's important to emphasize that the non-local influences, if you will, in quantum theory, don't produce new correlations. They consist of correlations that you can find later and after the fact, but they can't be used to create new correlations instantly across distances. There's a famous theorem known as the no signaling and no communication theorem. It's a little complicated to describe, but it rigorously establishes that given assumptions that hold for all known models in quantum theory, that no actual signals will propagate non-locally. This is important to make clear. You can't use quantum mechanics to send instantaneous signals.
Yeah.
Quantum mechanics bends relativity, but it does not fundamentally break it. And so what this means is that the non-locality suggested by, say, Bell's theorem, if you take seriously this non-locality, it doesn't lead to any direct contradiction with any observable results. It doesn't say quantum mechanics is definitely wrong, it can't be non-local. But if you're like some people, like Einstein was, who are uncomfortable with even a hint of non-local influence, even though it doesn't lead to contradiction with reality, even though it doesn't produce superluminal, faster-than-light signals, if you're uncomfortable with that, that's still going to be a source of discomfort for you. But there are a lot of people who say, oh, that's just prejudice. There's no reason we can't have influences that are faster than light as long as they don't lead to anything that could practically lead to a signal.
Yes, I had a question about, there's a lot of physical analogs to physics, and one of the aspects you're probably aware of is that GPS has long been kind of knocked. That what happens if one of the bands is banned by the military, no one can get around and no students can get to class, et cetera, including myself sometimes. So what happens if it is banned? There was talk, I believe, about using quantum acceleration, and then basically if you cool atoms down a couple of lasers, you'll be able to then measure the acceleration due to the mechanical properties of them, and that you don't have to use satellites anymore. You can get rid of the 66. But the devices are only going to be for, I would assume, for where you can use lasers, large transportation like boats, autonomous boats, cars, and even planes. What type of resolution could we expect using quantum mechanics for the actual positioning?
So that's a question for someone who's an expert in quantum instrumentation, and I'm not. Sorry.
Just happen to have one here. No, sorry.
Should I go? Okay. So you're talking about the charisma or lack thereof of some of the key players in the story. How important is charisma in the dissemination and figuring out of truth? And are there any theories today that you think get too much or too little attention thanks to their spokespeople?
Oh, that's a good question. I think I'm going to answer the second part first. This is going to maybe be an unpopular thing to say. I think that a lot of things that people say about evolutionary psychology are just getting way too much attention relative to their, quality. I'm not a psychologist, but I know a lot of psychologists and psychological researchers, and they're all pretty unanimous about this, and also it seems reasonably clear. How important is charisma and force of personality in determining the truth? I mean, science is a process that we use to try to figure out what's going on in the world around us despite our human foibles, right? And it tries to harness those foibles in the search for understanding the world around us. And it's never going to succeed entirely at, eliminating those things as factors. So I guess the answer is, it seems, it feels like it shouldn't play a role, but it does. Yeah.
If I may just add quickly to that, I think Einstein is a good example of this as well. The story you get, from this wonderful lecture is that, Einstein was up against very charismatic individuals, but Einstein was also a very charismatic individual, and there was a time early in the development of his theory of general relativity, his theory that united gravity with his theory of special relativity, in which there was a lot of discussion about whether his results were being empirically verified. There were arguments about whether his calculation for the weird behavior of the planet Mercury was really accurate, or whether it could be explained by other things. And he was just very confident. He laid his theory out there. He said, "I'm confident it will be confirmed." He made this very clear, and the force of his personality was very important. Ultimately, with further empirical investigation, his theory was substantiated, but it took a very long time, and his charisma, I think, did play a very good role. Even very, very good ideas sometimes need very strong advocates to survive the cauldron of early, experimental investigation. Yeah. So I think that's absolutely true.
Yeah.
This is a question about cognitive capacity.
Okay.
Dogs and horses and crows and dolphins are really, really smart, but they probably can't understand calculus.
Sure.
Could it be that there are limits to our cognitive capacity that makes it impossible for us to really understand quantum theory? And could you imagine beings of greater cognitive capacity, surely they might evolve somewhere, which could really understand it the way we understand calculus or special relativity?
Sure. Yeah, it's entirely possible. But I will say, some people, I've had some people sort of push back against some of what I've said in talks like this, saying, maybe we just can't understand quantum physics in this way. Maybe it's not a theory that we can understand in the way that you're talking about. And I guess my answer to that is similar to my answer to what you're saying, which is, yeah, it's entirely possible, but we have many candidate interpretations of quantum physics. The problem isn't that we don't have a way of understanding quantum physics. The problem is that we have too many. And so why give up? Why just throw up your hands and say, no, there's no way that the world could be that we would understand that would allow us to, understand quantum physics? Like the world can't be a way that our monkey brains can get around. Why do that when there are plenty of other candidate ways of understanding what's going on? So yeah, it's possible, but I don't see any compelling reason to give up yet.
There's a concept in the philosophy of science called pessimistic meta-induction. It says that we keep revising our theories every generation, and when we revise it, sometimes it feels like we're totally throwing out the previous theory. And if that's true, why should we believe even our current theories are accurate? This is pessimistic. Why should we believe what we have if historically we keep overthrowing it? I think the answer I would say to that is an optimistic meta-induction. There's so many times in history when we thought we were stuck, we thought we couldn't figure it out, and then we did. Then humanity figured out a breakthrough theory, transformed everything. This happened over and over and over and over again. So why should we think that this is the end of the road, that this is where we're going to stop?
Yeah. Let's do another question from this side, because I think we had two from this side before.
Just a heads up, we have time for one or two final questions.
Wait, no, we have another microphone up there, don't we?
Oh, I was just saying we have time for one or two more.
Oh, okay, yeah. Oh, well, whatever. It's fine. Let's take this question. Let's take this question and one more.
We'll go quick.
Yeah.
I was wondering if you're at all familiar with the work of Alexander Wendt. He's not a physicist, but he's a political scientist. But what he's come up with what may be a revolutionary theory that the quantum effects don't wash out at the subatomic level, but they work at the macro level, and that essentially humans are walking wave functions. I mean, if you know his work, then you could.
I'm only vaguely aware of it. The name sounds somewhat familiar, but I don't think that I can intelligently comment on it. I mean, some quantum effects don't wash out, right? We've got superconductivity and other things like that happen at all scales. but it's definitely true that we see some quantum phenomena at small scales that we don't see on big scales. And that doesn't really seem to be up for grabs.
So here's what I want to do. Yeah. I really want to thank, before everybody leaves, I really want to thank Adam Becker and Jacob Barendess. I think I have to just tell you that when Adam was speaking, I thought, wow, he's making quantum mechanics, physics seem really exciting, like when I was a kid. And I just thought that it was wonderful to be there. And also, I think you notice now that, how good Jacob is at explaining stuff. So if you ever want to know anything about physics, he's here. So I wanted to thank them, and I'd love for you to come over and have a piece of cheese and a cracker. And, Adam is going to be there signing books and selling books, and I'm going to be there just hanging around. Okay, so thank you so much for coming.
Have a good night.
Thank you.
It was wonderful. Thanks. Good work.